Now we're going to look at exponential and logarithmic applications. The first problem we're going to look at is about bacteria, and I think bacteria is cool. But anyway, well, I know E. coli is not cool, but just bacteria in itself is cool. Alright, the number N of E. coli bacteria in millions per milliliter after t minutes can be modeled by this function. So N of t, this is my number of E. coli, and t is time in minutes. Determine symbolically the elapsed time required for the concentration of bacteria to reach 25 million per milliliter. So now we've got to figure out where to put the 25. Couple of things that clue us in here. It says we needed to find the time, so we need to find t. And also they tell me that this is the number of bacteria. So the 25 is going to go in for N of t. Well, now this is an exponential equation. I'm going to have to remember, get my base raised to unknown exponent isolated, so we're going to divide both sides by 0.5. Now if you remember, we've got to free out this exponent, so I'm going to take natural log of both sides to free out the exponent. When we do, something nice happens because natural log of e is equal to 1. Only other thing I've got to do here is divide both sides by 0.014. So I end up with t approximately is 279.4. Well, what that is, that's how many minutes it's going to take for this culture to get to 25 million per milliliter. So the elapsed time required for the concentration of bacteria to reach 25 million per milliliter is about 279.4 minutes, or 4.7 hours. E. coli is not good bacteria, and they really have a good time. So they grow fast. Got to watch out for them. Next problem. The number of individuals waiting for liver transplants can be modeled by this function, where X is the year. And the source here is the United Network for Organ Sharing. So they want us to estimate this number in 2005. Well, guys, 2005 is my year, so that's X. So all I need to do is find F of 2005. So store that in your calculator. And type in the function 2340 parentheses 1.124 raised to. Now since my exponent is a binomial, I got to put it in parentheses. Minus 1988. So how many people are waiting for liver transplants? Looks like about a little over 17,000 approximately. So there were about 17,070 individuals waiting for a liver transplant in 2005. Now, when you are given applications, you've got to know, and they have to tell you what your Y represents and what your X represents. Now, determine symbolically when this number might reach 30,000. Well, guys, when it says determine symbolically when means time. So what year are we looking at? So 2005 is a little over 17,000. So now in this problem, I've got to put 30,000 in for Y. So let's go do that. Whoopsie. Here's base raised to unknown power, so I'm going to divide both sides by 2,340. And probably if you put 30,000, let's put 30,000 in. And divide by 2,340. I'm going to first hit enter. Notice it's not really a nice decimal, so if you go frac it, that's where that came from. So the base raised to unknown exponent is isolated. So now I need to take log of both sides, and knowing me, I've done ln. Yep. to free out the exponent. And if you remember from the logarithmic equations, I'm going to divide both sides by this right here. And then add 1988. Yo. So this can all be put in your calculator. Let's go for it. I've got natural log. I've got 500 divide by 39. That's my numerator. Divide by natural log of 1.124. And then add 1988. So let's see if that's what I've got right here. Yep. So now, when you have word problems, you need to go answer them. So sometime in 2010, the number of individuals waiting for a liver transplant will reach about 30,000. Wow. Okay. So I've got a few more problems. Now it says for problems 3 and 4, estimate the time for P dollars to double. So they're giving me my the amount that's going to be deposited, and they want us to find the A value. So now in this problem, it's compounded quarterly. So that's my A equals P parentheses 1 plus R over N raised to the NT. So let's plop the stuff in where it needs to go. The 1,000 goes here. Now when it says for it to double, that means this is 2,000. So I've got 0.085. Quarterly, remember, is 4, so I'd have 4 here and here. So they ask us to estimate the time, so the only thing I've got left that I don't know is T. Okay, let's clean this up a bit. We can divide by 1,000. We can also simplify the inside. Let's see, 1 plus 0.085 divided by 4. That'd be a whole lot nicer to write than that. Whoopsie. Okay. So take natural log of both sides, or take log if you want to be different. Oh, went too far. Free out the exponent. So now I need to divide. Now if you'll notice, the 4 is multiplying the t, as is this log. So I need to divide both sides by 4 and natural log of 1.02125. And notice I do have it in parentheses because you have to have that. So put that in your calculator, see what you come up with. And hopefully you came up with that. So I've got to write out what we're talking about here. It should take about a little over 8 years, 8 and a 4th year, for that 1,000 to get to 2,000 at that interest rate and being compounded quarterly. Okay? Another one, continuous compounding. That's your shampoo formula. So my P would be 750, which means A would be 1,500, R 0.12. So plop the stuff in where it needs to go. Remember, base raised to exponent, I've got to isolate base, so divide both sides by 750. And guys, this, you know, I ended up with 2 over here and here. It's going to happen every single time. If they wanted us to triple, then I would end up with 3. So take natural log, for sure take natural log of both sides here. Bring out your exponent, and we're almost done. Divide both sides by 0.12. Afraid I'll go too far. And if I put that in my calculator, natural log of 2, divide by 0.12. 5.78 years. So if we say it's sort of similar to this one, it will take about 5.78 years for the $750 to double given these conditions. And that's it. Thank you. Bye-bye.